All right, everyone. Well, welcome to our next session. My name is Latara. I am the talk manager for RustLab this year. I'll be facilitating the sessions and helping out with the Q&A after the video. We're going to be watching a talk by Michael Yuan on the state of WASI support in Rust and WebAssembly toolchain. So I'll read the short bio and then we'll go ahead and watch the video. So Dr. Michael Yuan is the author of 5 books on software engineering. His latest book, Building Blockchain Apps, was published by Addison Wesley in December of 2019. He is also the CEO of Second State, a company that focuses on bringing WebAssembly and Rust technologies to the cloud, blockchain, and AI applications. Prior to Second State, Dr. Yuan was a longtime open source contributor at Red Hat, JBoss, and Mozilla. Outside of software, Dr. Yuan is a principal investigator at the National Institutes of Health with multiple research awards on cancer and public health research. He holds a PhD in astrophysics from the University of Texas at Austin. Not crazy about the boy bands for Korean boy bands. He much prefers Korean hip hop. So about our talk today, the WebAssembly Systems Interface, WASI, is one of the most exciting features in WebAssembly. Docker CTO once said it was the future of computing. Rust provides the best toolchain for WebAssembly, but what about WASI? The Rust and LLVM compiler toolchain provides excellent support for WebAssembly. However, while the WASI interface is one of the most excellent features of WebAssembly, especially in use cases outside of the browser, WASI and wasm-22 WASI are unevenly supported across the compiler and runtime landscapes. So in this talk, we'll cover topics such as WASI support in Rustc and Cargo, Reactor modes in Rustc and LLVM, WASI support in wasm-bindgen, WASI support in Node.js, WASI support in Deno, WASI support in leading WASM VMs, and then we'll cover the current state-of-the-art as well as future directions for it. So I just want to let you know before we listen to his talk, the video for that, if you have questions to ask, please direct them towards the chat bubble that has the question mark under it. So if you see the headline for chat, you have the room chat and the question mark icon. Please ask your questions there just so that we can keep things organized. And then we'll bring him on later on to answer your questions live. So stay tuned, enjoy the video, and we'll talk to you in a little bit. Thanks.
Hi everyone. Nice to meet you online. My name is Michael Yuan, and I'm the CEO of Second State. So this you can see here is my home office in Austin, Texas. So I live in the USA. And the topic of this talk is Rust and WebAssembly. So let's get started now. I'll share my screen. Okay, so hopefully everyone can see my screen now. WASI stands for WebAssembly System Interface, and we believe this is one of the very important features of WebAssembly, especially concerned with its interaction with other high-level languages and the low-level operating system. So we're going to talk about that later. So the company I work for is called Second State. It's on this slide. So what we do is we are a fully open source company. We provide open source implementation of WebAssembly. How is that different from other WebAssembly implementations? That our focus is server-side applications. So we don't optimize our WebAssembly runtime to run inside web browsers and things like that. But instead, we optimize it to run on the server. Server includes, cloud computing servers like function as a service, the serverless computing, servers on the serverless computing, and also blockchain systems. So those are the areas that we focus on. We optimize our WebAssembly runtime for those tasks. And in the process, one of the most important tools that we use is WASI. We're gonna look at it and discuss its support in the Rust ecosystem throughout this talk. So, so without further ado, let's look into what's our talk. So the first question people always ask is, why do you compile Rust to WebAssembly? We all know that Rust is a highly efficient and memory-safe systems language, right? So you can compare it to native applications that are going to run natively on Windows or on Linux, mostly Linux, I suppose. And so why would you compile it to another target, to WebAssembly? That is, have its own virtual machine, and you're going to run the compiled Rust code in that container, and which could potentially harm its performance. And so why would someone do that? Why don't you just run the bare metal? Right? So that's actually, the same question that has happened in the computer industry, in enterprise computing for the past like 3 decades, right? So I'm old enough to remember when Java first came out. People had the same question, because back then you can run server-side applications using C++, Apache web servers, right? And you can also write server-side applications in Perl. So why would someone write it in Java? Isn't Java something that's invented for running those little games inside the browser? It's pretty much the same use case that people talk about WebAssembly today, right? After a couple of years, the fact speaks for itself that Java has won on the server side, at least for a time. It's becomes the mostly widely used application language that when people want to write database applications on the server, they use Java. So we think WebAssembly has the same kind of opportunity for the exact same reasons. So I list some of the reasons here. So the first, perhaps most important, is safety and runtime isolation. As we all know, Java, Rust provides at the language level provide memory safety, but you can still make mistakes, and you can still do things that would make the application crash at runtime, right? So runtime safety can only be guaranteed in the runtime sandbox, and that's especially an issue when software becomes more complex. So even if inside enterprise IT departments, you have different people writing software, there's no way for the IT folks to evaluate every piece of software that's coming from developers and make sure they are right, they wouldn't crash. That's to do formal verification, things like that, to verify its behavior. So there has to be a way that guarantees the software written by different people won't interfere with each other. If something crashes, it wouldn't crash other components on the same system, right? So even within an organization, you have this issue that you have to containerize or running software from different people in sandbox to guarantee at runtime they do not interfere with each other. And even more importantly is, as cloud computing takes off, more and more software runs on the cloud. When you run something on Amazon, AWS, for instance, right? AWS would have no idea who wrote this software and what's the quality of this software. All they do is they take the software and run it, and that software could crash, could do a lot of different things, and it should not interfere with other people's software. So to run untrusted, unverified code on the server has been a great need in enterprise for the last 30 years, and it has not gone away because Rust was invented. Rust solved some very important problems in C and C++, but it did not solve the runtime isolation and the runtime security, the safety problem. So that's why in order to run applications in a safe enterprise environment, you still need some kind of sandbox. And WebAssembly has emerged as one of the most appropriate or most I would say the most performant and the most widely used sandbox environment for Rust applications. So that's the first. I think that covers the first two, right? Safety and security are related, but they're not the same. Safety could be caused by a bug or caused by edge conditions, and the security could be something that people would just want to hack the system. They would write something, and so for instance, in the public cloud environment, if I'm a black hat hacker, I could write an application like try to steal data from other people who runs on the same data center. Right? That's why all the application needs to be containerized. It has to run its own sandbox. So even if it wants to do something, it would not have the opportunity. Right? So WebAssembly provides this opportunity for us to isolate Rust applications and allows them to run in a shared server environment, either in a public cloud or inside an enterprise. Now, of course, there's portability. There's even on the server, there's many different architecture and many different operating systems. You have Linux, you have ARM-based processor, you have Intel-based processor, you have custom processors these days for applications like AI, you have GPU, CPU, you have all kinds of stuff, right? So to have application to write once and run anywhere has always been one of the requirements or one of the demands that IT people would have. So that when they upgrade software, when they upgrade hardware, your application would continue to run. They would not have to recompile it, or worse, cannot recompile it, and you have to go back to the developer to say, we just upgrade our Ubuntu, the libc's updated, so your application wouldn't run. And could you, and you wouldn't even be able to recompile it. So would you go back to change the source code and do it and make it run, right? So portability is one of the huge issues that may not that's I think it's also an issue on the client side. That's when you run WebAssembly applications in the browser, it also has the same issue, right? Because when you distribute that binary, customers are going to have different computers. But it is what I want to say is that a huge issue on the server side as well. Although people tend to think on the server there's less variation of computers. And also less variation of operating systems, because the IT department or the cloud provider can specify which are supported, which are not. But the range of being supported hardware and software is so wide that portability is one of the most important issues in enterprise computing. And of course, there's manageability. That means I would need the ability to start, to stop, to reload, to hot swap the application without shutting down the whole thing, without shutting down the whole server, right? The server may be running 1,000 different applications. I would need the ability to reboot just one. So, and be able to move this application from a congested server to another one, to one that's less busy, to another data center, to do things like that. So those are the features that we would need that WebAssembly as a sandbox environment would provide us, right? So lastly, which I think is also very important, is WebAssembly provides JavaScript interoperability. So here's a quote from Jeff Atwood, who's a founder of Stack Overflow. And Stack Overflow is a website we all use every day, right? So his words are important. So he said, an application that can be written in JavaScript will eventually be written in JavaScript. That's how popular it is, because for millions of developers, that's the first language they learn, and that's also the first language they get productive, because everybody starts with creating a website, right? That requires JavaScript. So as you can see, there's many JavaScript frameworks that become very popular. So in order for a Rust application that performs heavy-duty computing to be incorporated into popular to be accessible to millions of developers and to be incorporated in popular frameworks, it has to play nice with JavaScript. And today, compiling Rust to WebAssembly is perhaps one of the best ways to ensure JavaScript interoperability. We're going to talk about that in a minute as well. So now we have established there's a reason to compile Rust source code into WebAssembly bytecode, and we can certainly do that. That's people have been doing that for a couple of years now. So what's missing from the WebAssembly VM? Why are we still not satisfied? Why are we still looking for new solutions like WASI or second state, right? So perhaps the most important thing is WebAssembly is designed to guarantee safety and sandbox. So it's a very, very simple computer. It's I would say it's a computing machine. It's a state machine. It's not really a computer. For instance, it's all the internal states is deterministic. So there's no random numbers because it doesn't have any concept hardware. It's a pure software VM, right? What does that mean? That means you can't do cryptography applications, right? You can't generate random numbers as seed or generate random private keys, things like that. You don't have that because the WebAssembly VM does not really have a concept of a physical CPU. It doesn't have a concept of what time it is. It doesn't have an entropy source that would give randomness. So everything is deterministic. And also, it's a compute engine, so it doesn't have a concept of a file system. You can only put data into memory and compute it. There's no notion to say there's a hardware, some hard disk somewhere that there's a hierarchical file system that you can go there and get data. And it does, of course, it also doesn't have a concept of database or object store, any of the advanced concepts that related to data and file storage. And it doesn't have network, it doesn't have socket, because those are all features that the computer itself provides. It's not the computer engine, it's not the CPU providing those features, right? So, and even more, it does not have access to the underlying hardware. So everything is abstract for the software at the WebAssembly level. So in that level, you see a CPU that can perform computation. You don't see how the computation is done. So you don't know the underlying hardware is, say, Intel or ARM, or is there a GPU available? Is there an AI chip available? Whatever the fancy hardware is available today in the data center. That's both a pros and cons. In the pro side, that means WebAssembly applications are truly portable. Because all the hardware details is being abstracted away from it, right? So the WebAssembly application does not need to know what's going on with the hardware. But on the other hand, it defeats one of the primary goals of using Rust and WebAssembly, which is performance. Because today, in order to achieve high performance in computing-intensive applications, like in deep learning, AI, or in machine learning, you need to have coordination between software and hardware. You need to make full use of the GPU if it's available. You need to make full use of the AI chip if there's tensor operations and things like that. So those are the current issues with WebAssembly itself. It's just to say it is more of I would not use the word toy, but it's a software-based computer engine. It's not a real computer. So you can't write full-blown application on it. You can only write fragments of applications on it, as a lot of people do today, right? So then the other part of it is people want to write full-blown application on it. So where does all those functions go? It goes into the toolchain. So that brings up the second issue, is that today's WebAssembly VM, especially from the Rust and C++ perspective, have heavy dependency on the toolchains. If you have ever compiled a Rust application into WebAssembly and call it from JavaScript, or compile a C++ application into WebAssembly and try to use it in JavaScript environment, you'll find the compilers generate a huge amount of JavaScript code. We call it glue code. It glue together the host environment with the WebAssembly VM. So the WebAssembly VM stays simple, but all the exchange with the host environments is handled by the generated glue code. So they construct memory and then pass those memory into WebAssembly, and then take memory outside of WebAssembly and pass it back to the host. All this so that WebAssembly would be able to, the WebAssembly application would be able to call some basic functions from the host. So for instance, if you are writing a WebAssembly application that's going to manipulate, say, a web page, right? The canvas on the web page to draw something on it, you need to interact with the host JavaScript environment. But because WebAssembly by itself is not a full computer, it's just a computer engine. So all this interaction between the JavaScript engine, web page, and WebAssembly has to be generated by the compiler. The compiler generates, certain amount of WebAssembly code, but an even larger amount of JavaScript code in order to do that. And that's, in our opinion, this is less ideal because that feels like something you hack together, right? It's to have a compiler, to have a clean, elegant compiler like Rust, and then generate a bunch of JavaScript code that's nobody be able to understand. I wouldn't say nobody be able to understand. Few people be able to find those code are clearly intended not to be modified by humans, right? It's generated by the compilers. So those are, I think, those are the issues that that we find, that limits WebAssembly's adoption in the real world. So the answer for those questions is WASI. So back in 2019, I think that's a year and a half ago. That's more than a year and a half ago. Mozilla's Lynn Clark made an announcement that there will be WebAssembly runs outside of the web has a huge feature, and that gets a great leap forward because there's a system interface for running WebAssembly outside the browser, outside of the web. And what is the system interface for running WebAssembly outside of the web? Is to make WebAssembly a more full computer. It gives you access to the operating system and other host environments for your WebAssembly application without all the hacks that I have just mentioned, right? So immediately following up, Solomon Hykes, he's a creator of Docker and the first CTO of Docker for a couple of years. And he said, if WebAssembly and WASI has existed in 2008, we wouldn't need to create a Docker. That's a very strong statement. That's how important it is. WebAssembly on the server is the future of computing. Docker is a tool that we use every day. It performs some of the same functionalities that I've talked about as WebAssembly, right? The primary feature is isolation and security. Is that you have an application that you need to run it. These are either on your own computer or in the internal system, or in the internal IT system, or on public cloud. In all three of those cases, you don't want it to interfere with other software that's running on the same hardware, same machine, right? So that's Docker provided isolation that allows you to run those applications in its own container or its own sandbox. So so you'll be able to make changes. You'll be able to run it with you wouldn't worry about its interfering with other applications. That's what I'm trying to say, right? So WebAssembly, like I said in the early slide, it's have pretty much the same features for Rust applications or for compiled C++ applications, right? So that's why he said, that's if this has existed, we would not need to have created Docker. We would have just used WebAssembly. Is it exaggeration? I think in 2019, WASI holds great promise, and that shows the optimism. That shows people have high hope for it. So in the past year and a half, a lot has happened with WASI. I think we have moved the spec and moved the implementation forward by a lot. And is it at the point where we can replace Docker with WASI? I wouldn't say definitely, but for a lot of applications, I think it's becoming a reality, which I'm going to show you an application that we developed later, which is artificial intelligence as a service, the server-side application that performs TensorFlow on custom hardware, right? That's for something like that, we can now use WebAssembly to do it instead of using more heavyweight stuff like Docker, which, of course, there's a lot of people love Docker, but one of the issues with Docker is the large footprint, and also it needs to bootstrap the entire operating system and the software stack on top of it. So the code start time is slow, and it has its own problems. And WebAssembly resolved a lot of those problems by providing a high efficiency, highly abstract runtime environment for applications. So that's why we like WebAssembly and why we like, we like Docker and we like WebAssembly. We sometimes use them together, right? But that's a slide that has been used. I have seen it used in conference talks a couple of times this year already. It's to say the WASI standard is super important for WebAssembly's adoption on the server side. So, like I just said, the key functionality of WASI is this paragraph. So it provides you access to the operating system features like the files and other external systems, the environmental variables, the random number generator, the clock, all kinds of stuff that the operating system provides for a computer that you can now access inside of the WebAssembly VM through an API. And so if the WASI just standardized that would be a huge accomplishment. But one of the things that get people excited about WASI is it goes one step forward. It does it in a way that is secure and provide a new security model that has been discussed in over 30 years, but has never been seriously used in real-world operating systems. It's called capability-based security. So we know the operating system security is mostly based on access control list, right? It depends on the privilege my username has. So if I'm running a server-side application as user XYZ, it's gonna be able to give me access to all the file systems and all the functionalities the computer has allocated for the XYZ user. I can't further refine its access. The capability-based security model is different. Is that as user XYZ, I start a new VM or a new, in this particular case, a WebAssembly VM. At the time of starting up, I would be able to specify what are the things that I access. So for instance, here is the JavaScript code in Node.js. The experiment, this is in Node.js 14, they have experimental support for WASI. So here is how do you start a WebAssembly VM inside JavaScript using capability-based security. You can see there's a construct at the top said WASI. The WASI has, say, the arguments, which refer to the command line arguments. The environmental variables that's typically available in the operating system. So for instance, the path variable, the home, all kinds of stuff. In your typical Unix operating system, you print out the local environmental variables, you get maybe 20, 30 of them, right? It describes what's the environment of the operating system. The pre-opens are the directories of the file system that the WebAssembly runtime would have access to. So the runtime does not have access to all the file system directories that my user has access to. It only have access to the directories that I specify at the time when I initiate the runtime, right? So here, when I create a instance of the WebAssembly VM by calling WebAssembly.instantiate, it creates a WebAssembly and using this WASI object, and this WASI object specify what I have access to. So that's, in a nutshell, that is capability-based security. So it's a new security model that allows us to do more refined control than the operating system itself, right? So that's also one of the features that get people super excited about WebAssembly. It's one of those things that people have, in operating system, people have talked about this new approach for years and years, but no one has really done it because everyone's using the same old operating system. Even with Docker, it uses it basically starts a Linux operating system for you in a container. It's still Linux, but in WebAssembly, we have a higher level of abstraction, so we can take the security and safety to the next level. That's very in sync with the ethos of Rust, which is provide more secure, more refined security control, safety control for the programmers and for users. Right? So that's the capability-based security is an integral part of WASI. WASI is not just standardized access to operating system, but also standardized in a way that we thought it's gonna it fits the ethos of the WebAssembly and the Rust community. So we try to do it the better way. So before we go on to the details of WASI and how it is done in different WebAssembly implementations, let's look at a typical server-side application that's today, right? So on the front end, you probably have some high-level language framework. In our case, we use Node.js and JavaScript as example, like I said, because perhaps 80% of all developers in the world are already familiar with JavaScript. So that's also the logic behind Node.js, right? So people say Node.js is a JavaScript runtime. It's not. It's a C++. Well, it's written in C++. It just runs JavaScript applications, right? So the user application comes in. It's written in JavaScript and in WebAssembly. So it's there are some functions that are interpreted by the JavaScript interpreter and run as JavaScript code, and those are those functions obviously would run very slow because JavaScript by itself is a very slow language. So anything that needs computational intensive, processing would need to go two ways. Either it goes to the C++ based runtime, so we call C++ module. So for instance, in Node.js, if you want to do image processing, it's a JavaScript function call, but it actually being delegated to a C++ library that actually does the image manipulation because it's it's 1,000 times faster than the JavaScript to do the array and data manipulation directly, right? So that's, however, like what we just said, to do everything in C and native has this issue of, if this code is written by someone else or even by myself, but I may not even have the confidence to fully run it on the server, together with other people's code in the full native mode, just to have too much privilege and too much, there's not enough control that would let us, to have the peace of mind to say this code can run safely, right? So for well-known libraries, well-tested libraries like image manipulation, you can do that. But for application in my own logic, that I would probably opt to write it in to compile it into WebAssembly. So from JavaScript, instead of delegate to the native library, I delegate to a WebAssembly runtime. And this WebAssembly runtime in the past is very limited. It only gives you compute. But now with WASI, it gives you access to the operating system. Because you have access to the file system, you can also access to database now. You can access the socket. You can, and then we're going to talk about that later in the slides, is that WASI is not, the WASI as a standardized operating system access, but the concept behind WASI allows us to extend the WebAssembly virtual machine to access other host environments, which we're going to talk about in a minute. But here we're going to just say AI hardware. If your server have specialized hardware like the Google TPU, right? The special processor for the TensorFlow, have those installed. You could access them the same way WebAssembly use WASI to access the operating system file system, right? You can have what we call AI WASI or TensorFlow WASI or GPU WASI, TPU WASI, to have an extension of WebAssembly that provides standardized and safe capability-based security access to those underlying operating system features. So I think that's one of the huge promise the WASI spec brought to us. It's not just to make WebAssembly more like a computer. It is, that's by itself is super important, but it's the way it does things. It opens door for us to do it in other ways as well. So so that's we're going to explain that in a minute. So let's look to the next slide. So Before we look at WASI applications, and to give you an example of how WASI actually work, how WASI is actually used, let's look into the implementation of WASI in popular WebAssembly runtimes. How exactly is WASI being implemented? So the first is actually, I would say, the old way, JavaScript bridge. As I said, today, a lot, if you compile C programs to WebAssembly or Rust program to WebAssembly using wasm-bindgen, you would get a lot of JavaScript glue that communicates between the JavaScript host, typically in the browser or maybe the Node.js, with the WebAssembly module. That allows WebAssembly to access different features from the host. WASI can be implemented this way as well. So it would rely on the JavaScript glue generated by the toolchain. So the toolchain would compile Rust, but also generate a lot of JavaScript glue that allows them to communicate with each other. So use those JavaScript calls to access system calls within. So when WebAssembly detects a WASI system call, it would delegate to a JavaScript call, because it knows itself running inside a JavaScript environment. So it would be able to do that. And that's a great example is Google V8, right? V8 running in the browser, in Node.js, in Deno. It knows itself always have a JavaScript. It knows it always runs in a JavaScript host. So it knows that if I encounter a system call, I can always reliably pass it to JavaScript, because JavaScript can open a file, JavaScript can access a random number generator, can do all that. So I can do that and get the result back into WebAssembly. So that's, like I said, that's Deno, Node.js, and most web browsers do that, because it's guaranteed the WebAssembly application is running inside JavaScript, and it's inside the JavaScript host environment. So all the system calls can be translated and delegated into JavaScript. Well, that's good, and that's that's how people do it today, right? So that's in this regard, WASI standardized this approach, to say, that's instead of having to remember, having to explicitly call JavaScript, you can now just use Rust standard library, and all those functions can be translated under the hood to JavaScript for you, so you don't have to. So for the developers, they are using Rust standard libraries. They don't need to know it's calling JavaScript under the hood. So that's a benefit of WASI in this approach. However, the problem with that, of course, is the performance is slow, because you have to jump out of the WebAssembly runtime to call JavaScript. JavaScript by itself is slow, and then the results has to be formatted and has to be passed into memory and has to be passed back in WebAssembly. So there's all those exchanges, and that's not really optimal. So that's one side of the story. So the other side of the story is to say, I want to run WebAssembly in a operating system environment that's may not necessarily make assumption that there's JavaScript available. So I would run on the standard OS operating system library. So the operating system library has standard libraries. On Linux, it's libc++, right? So in the WebAssembly bytecode, there would be no calling of JavaScript. I would pass calls directly to the libc in the OS. And why would you do that in the browser? It's because in the browser you can't assume that the underlying you can't assume you have access to the underlying system call, right? So, but for WebAssembly that's running on the server, I can make this assumption, and I can do it a lot more cleaner, right? So if I have a WebAssembly VM outside of the web browser, outside of the JavaScript environment, although it could be inside the JavaScript environment as well, and it would run a lot faster if I just take those WASI calls, the system calls, and translate them directly to operating system calls, the standard library calls in the operating system. And the benefit of that, the first is it makes the code much more cleaner. It's now we have a clear path of from Rust source code to WebAssembly bytecode, and from WebAssembly bytecode, I either drive the WebAssembly machine or I delegate it out to the operating system. Standard library calls. There's no JavaScript in between. There's no glue. It's a very clear path, and it's all very high performance. So it's good, and it also opens the potential for optimization, because one of the interesting one of the most effective optimization strategies you can have on the server side is called AOT. What is ahead of the time compilation, which is what we do at second state. That's why our if you look at the benchmarks, our open source WebAssembly virtual machine is by far the fastest, compared with all the other competitors in the market, essentially, because we do AOT. AOT is is to say I have WebAssembly bytecode, but I know I need to run this bytecode over and over again, which is a typical use case on the server, right? You have one application you're going to run it a million times. So I pre-compile it before the first time I run it. I pre-compile it into machine code. So every subsequent time I run the machine code only. I don't run the WebAssembly interpreter anymore. So I build all the security, build all the checks, build all those things into a web machine code binary. That's called AOT. With the streamlined process of the WebAssembly bytecode calling the native libc code, we can do the AOT compilation because there's no JavaScript in the middle. We can just link all those C-based native language libraries together and build the machine code this way. So that allows very aggressive and very heavy optimizations on our side to build much more efficient WebAssembly runtime for the server applications. So here, let's give an example. That's I talk. Those most high-level stuff, right? So let's give an example of how WebAssembly is implemented. WASI is implemented. Sorry. So with WASI, you can write applications like this on my screen. So it's a main application. So it has a main function. So it can be invoked from the command line. It executes the main function and then quits, right? So as you can see here, it uses all those Rust standard libraries to get random numbers, to get environmental variables, to do the I/O, to do the file I/O, read it, write, and to do all this. And it looks just like a regular Rust application that you would compile to the Linux environment. In the past, if you compile this to WebAssembly, it's gonna complain and create an error. But with WASI support, you will be able to compile this whole thing into WebAssembly. And now, like I said, in different VMs, it's gonna have different approaches. So for instance, if you run Node.js and Google V8, when it encounters a file open operation, it delegates out to the JavaScript to do the file reading. But with other implementations like the second state VM, what you would see is that it would call the operating system's libc and to open the file directly and get the data out of it. So that's the what I would say a complete example of WASI, right? That's you have the main function, so everything starts from operating system level and that's the operating system level. So that's and you have access to all the standard libraries. So that's something that's already done today, and you'll be able to, and I think all the leading WebAssembly runtimes has already implemented that. So here's a URL with the source code. You can download the source code. There's instructions on how to run it. You can see it yourself. It all works, and you can also compare it with if you don't have WASI. Say if you set your Rust compiler to say don't use WASI and use just the plain WebAssembly, use non-WASI WebAssembly, you would be able to find this code would not compile and would not run because that's because the standard WebAssembly does not provide this the functionalities like the file system. Okay. However, this is not the end of the story. Like we just said, today few people use WebAssembly to write the entire application. People use WebAssembly as part of the application, right? So if you remember the diagram I just showed, the front end is often JavaScript, and from JavaScript you can go different routes. The native routes for some functionalities, WebAssembly for other functionalities. That requires to embed WebAssembly into another environment. So we can't have a main function because the main function is you have a complete computer programs from the operating system that does everything inside WebAssembly. You can use the main function. So for this particular case, we need to embed WebAssembly as a library or library functions into another system, like in Node.js or in something else, right? So the goal is to call WebAssembly functions from another system. And the problem is, unlike the main function, when the operating system initializes the main function, it can initialize a lot of things like environmental variables and things like that. So it has a procedure it follows. But for a library function, the operating system does not have the opportunity to initialize it. So as a result, there has to be a special mode that when the compiler generates machine code, it has to generate it in a way that it does the initialization work the operating system would otherwise do. So that requires changes in the toolchain. So on this side, and there a link, you can see this is a link we use to track those issues. All those are issues and PRs that made through different upstream projects of WebAssembly and WASI. So there's the Rust compiler, the WebAssembly target module in the Rust compiler, the WASI target module in the Rust compiler, the libc target module, and the LLVM, which is Rust compiles to the LLVM IR and LLVM further compile into machine code, right? So the entire toolchain, there are places that we have to fix in order for this we call it embedded mode or reactor mode to work seamlessly. And the good news is that all this has already been fixed. As we can see from this list, those are all accepted and merged PRs. They are all merged into the master branch or the main branch of their of each of those tools in the toolchain. However, they have not made their release. They have not made into the stable release. They are on the master branch, and perhaps it's a nightly build, but they have not been incorporated into stable. So that's we have this document to track it. Before they can make the stable, once they all make the stable release, we anticipate this to be in the next, I think maybe next couple months. Then this support would be seamless. Then you would truly be able to just write a library function in Rust, compile it in, and that library function going to use all the Rust standard libraries like file system and all that, and compile to WebAssembly, and then call it from another embed, call it from the JavaScript environment, right? That's going to all work. But before that, that's we would say that it does not work fully. So we need a workaround. So for C++, there's a workaround, but I want to talk about for Rust and the wasm-bindgen. We have another workaround. As you can see, here is the sample code that we have created for our other example. Is to say, I want to use today's stable toolchain and to embed WASI-enabled WebAssembly code in my application. How do I do it? It turns out it's not that difficult. There's we have created a Rust crate that's basically does all the initialization stuff for you, and then condense it into a single method. It's called _initialize. So incorporate that crate, and then you say, and then before you access the file system, you do the initialize. If you don't do that, the program is going to fail at runtime because, like I said, there's holes, there's gaps in the toolchain that would not generate the correct file system operating code for libc. But with initialize, it would be able to do that. So try it out. That allows you to write WebAssembly in a way that is intended, right? That's is to be part of the larger system. You write a WebAssembly and embed into, say, Node.js or some other server-side environment, and call the WebAssembly code from those from the host environment. You can do it that way. So there's also WebAssembly compatibility metrics, and there are tests you can run, and you can see, that's the short answer is because of those toolchain issues, there's none of them is actually compatible, fully compatible, although they all have different workarounds. But we hope this situation to be resolved in a month or two. So then there are things, I have maybe 10 minutes left. So I want to also talk about things that beyond WASI. The concept of WASI can be used to expand WebAssembly into different host environments. like I said, then again, it's separates out into JavaScript bridge, which is what people already use. That in Node.js, that if you know you are running in a JavaScript environment, you can say that that I want to call the host JavaScript by name. That's and so it can pass a string name and it go out and call that JavaScript function and gets a result back. It's a I think this is it's a hack. It's fragile to do it this way, right? So a better way is to do it as a host functions. Using the concept that's been developed in WASI, we can not just support the libc functions, we can also support other host functions. So let's give an example. On the blockchain, for instance, a lot of people use WebAssembly on the blockchain to execute smart contracts. Those are truly untrusted code. Anyone can submit those piece of code, smart contract, into the blockchain and ask all the blockchain nodes to execute it. And they have to do that in a way that's in a sandbox. And so WebAssembly is frequently chosen for this purpose. And but the interesting thing is the smart contract need access to the underlying system of the blockchain. For instance, need to know which block it is on, what's the timestamp it is, what's the balance of the accounts that involved if I want to transfer money from one account to another. And does account A has enough money to be transferred, things of that nature. So it needs access to this database, I would call the host environment. And that's a typical use case of host function. And we call it the Ethereum WASI or blockchain WASI, right? It's basically, you modify the WebAssembly runtime in a way that it would, or extend the WebAssembly runtime in a way that's similar to WASI, that when it encounters those Ethereum specific function calls, it would know to pass it directly to the host system instead of crashing, right? So that's one of the cases, and of course the data storage and OS level command, which we're going to talk about next. So the last couple of minutes, I just want to give you a demo of how we extended as a use case demo, how we extended WebAssembly to do AI as a service, in particular TensorFlow as a service, as I talked earlier in the talk, that the TensorFlow is often a native command, native to the operating system. So how do we call it from WebAssembly? That we call it in the same way that we use WASI to call the file system. That's so it's you can see the thinking is the same. It's just a different application use case, right? So there's a couple of live demos you can see, from our website. It's secondstate.io/fast function as a service. It's allow you to say upload the image and find all the faces on it, upload the image and find what's objects in it, things of that nature. On the backend, it all runs WebAssembly and TensorFlow. So it's so the function itself is written in WebAssembly and it's executed in TensorFlow. The flow is like this. So it's similar to the diagram that I've shown earlier. So there's on the front end, you have JavaScript that allows, Node.js features that allows you to upload files and, the web server and all that stuff. And then application logic is written in Rust and compiled to WebAssembly. So in this particular case, all the business logic, like how to resize the file, what's to detect the file format, resize the file, turn it into an array, select what model I want to run, and all that stuff, is what we call application logic. Is user written logic. It's untrusted code. It could have bugs. It could have security issues. They're all written in Rust and compiled to WebAssembly. And somewhere in the code, it needs to run TensorFlow to say, here's the prepared data and here's the prepared model. Run TensorFlow on the GPU for me. So that particular task is used. So we use a WASI-like interface to pass it to the native library. The native library runs it and gets it back. So instead of calling libc native library, we are calling a TensorFlow native library to do this particular task. So that's the idea behind it, right? So let's see how it actually works. So on Node.js code, it's very simple. It's upload a file and then it returns a string. It's a string that says what's in the file, what's the confidence level, right? The Rust and WebAssembly is a key part of this setup. So that's like I said, this is what we call the application logic. So there's 7 steps. The first, we load the image and resize it to what the model needs. And then we load the model because everyone has your own TensorFlow model. That's we use image recognition model. We all train our own image recognition models so that it can recognize things that are important to our application, right? Birds watching, flowers, stuff on the desk, whatever. Right? So that's the second is load the model. And the labels, what's the model, how to interpret the numerical results from the model. And the fourth step is to say, I want to run the model and the image in TensorFlow. And that's the WASI call. We leave it empty here because that's what we can describe in the next slide. So the fifth step is to, the WASI call has run the TensorFlow model on the GPU and got the result. And then in the fifth step, we capture the return value. And on the sixth step, we map the return value into the labels to interpret what the return value is. And number 7 is we return the value back to the JavaScript. So as you can see, 1, 2, 3, we prepare the data. 4, we make the WASI call to run the TensorFlow model. 5, 6, 7, we interpret what the TensorFlow result is. So all the application-specific logic is inside this file. All the WASI does is to run the TensorFlow in a standard manner. It's like open a file and read the file, something like, it's standard like that. So let's look at the next step is how do you run the TensorFlow model. And so here you can say I have a name for the TensorFlow model because there's many different types of TensorFlow models and they each take different input and output. We find it's easier to have a specialized command or application for each category of models. So in this case, we are running a MobileNet version 2 model. And in this, there's 4 arguments. You have to say what's the input tensor? Where do you want to put the input data? What's the output tensor? What's the prediction? The numeric values of what the object is, and the size of the input image. And then we pass in all the Then we pass in 2 pieces of data. One is a TensorFlow model, and the other one is the image itself. So we pass in all this through to the command, and then the command runs. There's just one single line. Call the command. It's command.output. It outputs the output tensor that we have specified. It gives it out as a data array. So it's so we capture this result and then continue to process it, right? So this so-called, we call it WASI command. It's not really WASI, but WASI-like command allows us to run a generic TensorFlow model. It also allows us to apply security to it, right? You can imagine when we start the WebAssembly runtime, we can say what kind of TensorFlow model command you can actually run. This particular program can actually run. So we can eliminate the programs we can prohibit certain programs from running any of this, right? So that's the idea, is to apply the WASI idea to other host functions. Then the TensorFlow command is very simple. It's just a matter of this just happened to also be written in Rust. It doesn't have to be written in Rust. You can write it in Python or write it in C++. It's all fine. That's but what it does is does the TensorFlow operation. It's a generic operation. It's unrelated to the application logic itself. To run this model, it does not prepare the data or interpret data, right? So it's suitable as a standalone application residing as a native application on the operating system. So anyway, so that's you can go on our website and see a demo, and you can also read those articles that discuss the architecture and the way that we do it. So we are also because we are open source projects, we also work on contributions because we have a AI model zoo approach to create those WASI wrappers for different AI models, right? You have we have face recognition, object recognition, natural language, and all that stuff. And there's many different categories of models, and each category has maybe thousands of different models people have trained. So that's we would like to collect all those on our GitHub. That's and to provide a comprehensive resource for people to run to call these models from their own WebAssembly applications. Right? So that's that's we'd love to have you participate in that and help us build a larger ecosystem, open source ecosystem for AI applications in using WebAssembly and WASI. So I think my time is almost up, and thank you very much for listening. And you have my email address from the conference and also from the first slide. Feel free to reach out or just contribute to our GitHub repository. Send us a pull request, send us an issue, tell us what you want to see fixed. And I'd love to continue this technical discussion with you after this conference. Thank you very much, and enjoy the rest of your day. Bye-bye.
All right, everyone, we are back. Hopefully you were able to see the majority of the video. Sorry if there were some difficulties. It always happens with technology, especially for this first live edition we're doing on Bizabo. We are ready to go live with Dr. Michael Yuan to answer your questions. So let's turn on his camera microphone. Hello.
Hi.
Welcome, Dr. Yuan. First of all, thank you so much for your contribution to RustLab. We're really happy to have you here.
I appreciate that. Thank you very much for having me here.
Of course, of course. Do you have anything you wanted to add about your participation in RustLab?
Well, yeah, this is my first experience conference, and in a virtual format, no less. So that's. But when we, I appreciate the opportunity for being here, and I know there's some issue with the video, but I want to point out that one of the major application use case for WebAssembly is to run video on the browser smoothly. So maybe we'll see that improve in the future.
Yeah, it's very relevant. Thanks. All right, so we're going to go ahead and proceed with some of the questions here. We've got one starting from Chris Greenaway. He says here, can you have resource limits applied to a WASM process, for example, GPU or memory limits?
Not right now. So it's so I think that's perhaps one of the issues of using WASI in a truly enterprise environment is that you can't really put a limit on the resource. I've seen people running WASI inside Docker, but that's kind of defeats the purpose, right? So but this is one of the interesting aspect of it is to have more operating system integration into WebAssembly. And to go with the way that WASI has done it is, in my opinion, is the right way. Meaning that's to have more, you have seen the sample code when you start up a WebAssembly virtual machine with WASI, you will be able to specify the file system directory it's allowed to operate in, and the environmental variables and things like that. So we could imagine that we can extend the specification to have it to say you can only run one CPU and 2 gigabytes of memory, something like that. But there's nothing currently available. So, but I think that's one of the directions it's going.
Yeah, hopefully we see something more about that in the future. All right, our next one is a two-part question by Arif. First, he says, I'm interested in using WASM to write apps in Rust for both iOS and Android with minimal OS-specific wrapper code and maximal efficiency. Is this already possible today?
Well, inside the browser, yes, because I think both Safari and the Chrome browser now support WASI. Well, not support WASM. Sorry, there's too many acronyms. They both support WebAssembly. That's. But the way they support WASI is through JavaScript. So so there still needs to have those tool chains that would generate those what we call the JavaScript grooves to go around and to go with your WASM code. That's why you see things like the WASM code compiled by one tool is not going to talk with the WASM code compiled by another tool, right? So but that's the inside of the browser use case. We talk about standalone free application. On Android, it's easier because the system is more open, so you can run another embedded WASI runtime, a WebAssembly runtime on it. So you can even run SSVM. So that's we have run a lot of those on, say, on Raspberry Pi. That's a very small device. It just has a very open operating system. I think Android can do that. I don't think iOS would be able to allow you to do that unless you jailbreak them. So in iOS, you'll have to stick with what Apple has, or do it in the web browser. So.
Okay. All right. Well, we'll see. Thank you. Next one is again from, the follow-up question before we go to Chris. Arif says, additionally, do you foresee this to be the dominant way to write cross-platform code in the future, or rather just another way to do so?
Well, I certainly hope it will be the dominant way, because, but I think, like I said, JavaScript is so popular. So, if you look at developer preference, most of them know JavaScript. And at least from this point now, I think most people working in WebAssembly agrees that WebAssembly supplements JavaScript, not replacing it. So, if you, to truly write cross-browser applications, you would have both JavaScript and WebAssembly. And on the server, it would be some other language plus WebAssembly. And the WebAssembly piece is mostly would be, at least at this moment, would mostly be provide compute-intensive operations. So if you have something that is too slow in Python, too slow in JavaScript, like we have just shown, the AI inference operation, I didn't actually show you a demo, but but we have implemented in JavaScript. It takes 30 to 40 minutes to run the inference. In WebAssembly with AOT optimization, it took half a second, right? So that's thousands of times performance improvements. So that's something that's going to be used first, and not necessarily, cross-platform UI applications, so to speak. The old days how Java was used. I don't think that's on the immediate future, But for the compute-intensive applications, that's cross-platform. Then definitely yes.
Okay, thank you for that. We have two more questions. Again at Chris, also about something. He says, is there a lightweight WASI runtime, for example, something lighter than Node.js?
Absolutely, yeah. So the problem with Node.js is its runtime is V8. So V8 is designed for JavaScript, so so it has to run JavaScript and WASM. But almost every other WASM compatible runtime, like we look at WASM time, Lucet, there's WAMR, which is specifically designed for embedded microenvironments, and of course SSVM, second state VM. And we have, like I said, we have run all of them in a $5 Raspberry Pi device. In fact, it's a $5 computer, and you can run those. You can never, that's I would consider them to be pretty lightweight. So yeah, V8 is pretty complex, but only because it's you cannot separate from the JavaScript engine. But for all the pure WebAssembly engines, you can there are some really lightweight options out there.
Okay, thank you. We have only a couple minutes left before the next one, so I'm going to close with this last question here from Arif. And he says, what do you think of the choice of the name WebAssembly, given that it's not really web nor assembly? Will this odd naming ultimately hurt its adoption?
I don't necessarily think so, because first of all, it does look like assembly. That's because it runs bytecode, right? So another misnomer name is serverless, right? If you say I want to run application serverless, and people love it because because when people first heard of it, they find it so counterintuitive. What is the web is very different from assembly, so the people want to learn more about it. I think that's where people started, and then they would find it interesting. It's either a strange name like that or a meaningless name like Java or Ruby, right? That people can't immediately tell what it is. If you say it's a programming language for the web, people will say, oh, whatever. That's but that's my opinion. So
Okay. Well, thank you for that. All right, you guys, that was the last question for this session. Thanks again to all of you, and of course to our speaker, Dr. Michael Yuan. Hopefully, we'll see you in the next edition of RustLab, whether it be live or something like this on the internet.
Thank you so much.
Thanks for being here. Thanks. All right, and you have a great rest of your day.
Yeah, you too.
Thanks.
Bye-bye.
Bye-bye. Okay, everyone, we are running over time, so we're going to just go ahead and go straight to the next one here. Our next talk is Anacro PC, an anachronistic PC architecture by James Munns, excuse me. And I just want to remind you all that if you liked this talk, you can rate it on the agenda page of the website. So I hope to see you in the next session, and if not, have a good rest of your day. Bye-bye.